Hello, my name is Sean McDermott, and I'm the Applications Development Manager here at 4D Technologies in Tucson, Arizona. Today, I want to talk to you a little bit about measuring in difficult environments using something called dynamic interferometry. Quick overview of what we're going to discuss today. I want to talk a little bit about, considerations and things you need to think about in terms of measuring in some of these more difficult 3D metrology environments and/or applications, and how dynamic interferometry works and how it can be used to measure in these environments. And then we'll follow up a little bit with some applications and what dynamic interferometry really enables you to do in these type of work applications. So one question I have to you, what challenges do the following metrology applications I'm going to show have in common? And first, we'll start here with a slide. You can see we've got the James Webb Space Telescope there on the right, and a couple of engineers up on scaffolding multiple meters away with an interferometer across the room in a clean room to measure. You can see there's quite a few considerations there in terms of airflow, vibration, thermal variations, and other considerations for that environment. Secondly, we've got another optical application where we've got a system on the left-hand side there in a cryo chamber and trying to perform some autocollimation tests on a telescope in a cryo chamber, an environment where you can't quite access directly during the test. In addition to this, we've got a couple other applications here, more industrial side. So we've got robot automation, where you're looking at maybe some polishing optics or something in an automated form in line. Ophthalmic applications, where you're looking at lenses and optical molds. We've got precision machining applications, where you're trying to get down into microgears and structures and look for weak points, striations, failure modes, as well as measuring metrology handheld, or maybe on large on wing or large engine or other type machine applications where you have to do quick inspections without having to disassemble the whole component. A lot of challenges there on all of these in terms of vibration, part access, temperature, and things that really can cause issues, especially when you're trying to measure using optical techniques or other non-contact techniques to ensure peak performance and non-destructivity to the part. Again, the answer that always have in common, like I mentioned, is a lot of these are very difficult to do in traditional optical techniques due to many factors. Environmental, as I mentioned, if you're trying to measure large mirrors and large structures, you've got a lot of vibration, you've got a lot of turbulence in the room. Temperature fluctuations, can cause changes in current and airflow, and so for non-contact methods and interferometric methods, that makes it very difficult to get good data. You also have to take into fact system design, right? Am I looking at something that's multiple meters big, meter class optics? Am I trying to get down into a tiny borehole where I can't really get a full profilometer in there? How do I get in? How do I access? And how do I measure the surfaces very quickly and accurately in a handheld type environment? And again, down to things like, operational constraints, where if I'm testing in vacuum or in a cryo chamber, I don't have direct access. With the larger structures, you get a lot of vibration, you're going to get turbulence and airflow, especially in measuring this, and you're still looking for, oftentimes nanometer level resolution of surfaces, surface shapes, and surface structure, as well as in, moving an in situ inspection where you're in a fab or process line, where you're polishing an optic or cutting a precision machining surface, and you need to look at the finish as you're going. You need to measure in line in the process. A lot of access points, a lot of vibration, and things to consider. So for typical interferometers where you need an isolation table or minimized airflow, very quiet, it's very impractical or in some cases impossible to do with typical methodologies. One method, as I mentioned, that is used to measure these types of things is using something called interferometry. And what interferometry is it's really the use of looking at light that comes, say, from a typical source that you can then pass through various surfaces. In this case, we have a couple of flat optics you can see here. And what you do is you look at how the light travels off of one surface with respect to the other surface. And by tracking the difference in distance that light takes, you can actually get what's called the interference of light that you can see here on the right-hand side, like in the thin films or in bubbles, where you get a spectrum of the colors based on the thickness of the film presents a different level of wavelength emitting from it. And you can utilize that path difference to really, determine the shape or the form of something, because the difference in path creates an interference pattern called fringes that you see here in the lower right corner. And much like a topographical map, you can use the spacing and the depth of those fringes, which are based on the wavelength of the light that you use to create that, to get an accurate measurement of that surface shape and surface height. Why interferometry is really ideal for these types of measurements is it's fast. It's an area-based type measurement that you can do over larger areas, and that area can be scalable as well as can your resolution with various optical setups, depending on the type of information and the type of resolution that you're trying to get in a particular application. Not only can you measure the surfaces, but you can also look at the transmission properties and transmissive properties of optical systems and in their entirety, looking at wavefront error and things like that through an optical system. So interferometry really works out well for a lot of the applications that I showed in the prior slides. So how does temporal phase shifting interferometry or kind of your traditional interferometry work? Well, what you do is you use, in often cases, coherent light, like from a laser, as we show here, and you can shine that light off of through a beam splitter and shine that off of multiple surfaces. So you can shine part of the light through to the test surface, the surface that you're trying to look at in terms of surface fluctuation or polish variation, and you can also reflect that off of a very well-known and controlled flatness reference surface, and then look how those two beams differ from one another. So if you take kind of a single snapshot where you emit light off of both of those, what you will get is when that light comes back off of your reference and your test surface, it will generate an interference pattern that you can see here. Depending on how far that light travels, the optical path difference across the test surface varies. You get fringes, and that shape in those fringes determine the shape and the structure of the surface. Now, how can I measure this? One image gives me kind of an intensity image to look at what that surface is. However, I don't really know if those bends and bows in the fringes that I see are a potential, dip in the surface or a hill or a bump in the surface. So what you can do is you take a number of scans where you actually translate the reference surface over some various path differences from the test surface, and you get a number of fringe patterns. And from these fringe patterns, as you likely know, you can use this information to look at the intensities and how they shift through relative phase over a given velocity with respect to each other. And you can use this information to, along with the wavelength of the light, to redetermine the structure based in terms of a height map in respect to how those fringes change over time. Now, this is great. It gives you information on the surface down to, like I said, the nanometers in some cases. However, in order to get through the scanning of each of those, it takes quite a bit of time, typically in the order of hundreds of milliseconds. And during that time, you can have things like airflow, perturbation, turbulence, somebody bumps the table, and those will cause, errors in your data. Now, where dynamic interferometry comes in, and that's what we do with a lot of our equipment here at 4D, is you get a snapshot measurement kind of using very similar technology. So instead of translating through, what we do with the light coming from your source is we use polarization of that light to kind of code the beams off of the reference and test surface. And so what we'll do is we actually will shine the light out onto the surface and the reference surface, and by breaking out the polarization states, we can actually use a customized phase sensor at the camera to look at multiple different polarization states simultaneously, essentially allowing us to get those multiple fringe patterns that you need to determine, how that shape is varying across the surface in time in a single snapshot. It only takes nanoseconds for this acquisition, and again, because you're acquiring all of the data in a single camera frame, you're immune to vibration, you're immune to other impacts that typically would cause effects and cause error within the data. And so by leveraging this capability to acquire all that phase information in a single camera frame, that really enables us to do a lot of measurements and perform these measurements in interferometry in environments that a lot of other equipment and interferometers cannot get to or access just due to the nature of the structure of the sample, the environment it's measured in, or things of that nature. How does this phase sensor work? So essentially what we do is we have a micropolarizer-based phase measurement where we embed micropolarizers in a particular array over the pixels on the camera. And it's very similar to kind of a color mask. So a monochrome camera is, a color camera is essentially a monochrome camera with red, green, and blue filters over the individual sensors or pixels in the array or in the sensor. And in this case, instead of using color filters, we use polarizer filters, and we orient those different micropolarizers in a set array at given angles to allow us to get the proper phase shift, if you will, or the proper setting between the different interference patterns on the surface simultaneously across the full array. It all, again, is acquired in that single frame, and these have to be matched to the arrays on the camera. But what this really allows you to do is this makes this a kind of compatible technique for multi-wavelength as well as broadband sources, not just coherent light, because you're really looking at the polarization state of the light going through each of the pixels across the camera. So again, being able to take this single snapshot, it really gives you a lot of advantages. As I'd mentioned before, you have vibration immunity in your measurement, which is huge, right? You can also measure very, very quickly, where you're measuring down, into, nanosecond range. In some cases, if you need to, you can go very, very fast. The other nice thing about taking the measurements in a single frame is that really turbulence kind of becomes your friend versus your foe. And how that works is, again, if you think about it as you're measuring with standard temporal interferometry, as you shift the reference mirror with respect to your sample, any perturbation or airflow in the environment that you see is going to carry right into print through in terms of where those fringes and that interference light goes, because the turbulence and the airflow can change, the relative index of the air you're traveling through and slow up or speed down the light, causing the fringes to vary. With dynamic interferometry, because you're taking that single snapshot, what that enables you to do is you can actually take multiple measurements very, very quickly, multiple snapshots, and average those together, where even if you have periodic or other airflow through the environment, by being able to take many averages very, very quickly, you actually can average or smooth out any of that airflow or perturbation or turbulence in the environment and get direct, accurate data. Along with that, I said because of those short exposure times, that allows you to do that. With that, you also can measure a broader range of intensities. So you can measure on highly AR coded components, highly reflective components, and there's no degradation in the performance at either of those ranges. That's reflectivity range is increased as well. So really what dynamic interferometry gives you is sort of the ability to measure optical surfaces and other surfaces anywhere you need it. On shop floors, in large clean rooms, in vacuum chambers, across optical setups that have large gantry systems and have a lot of vibration, you're still able to get good, accurate measurements of the surfaces and/or wavefronts in those types of setups. Now what I'd like to do is talk a little bit about some of the various applications where we've used our dynamic interferometers to enable measurements that weren't able to be done before. A lot of applications utilizing the dynamic interferometers are in the telescopes industry, where they're really looking at large polished optics, small polished optics, where you need extreme precision. Also, you need performance across a wide array of temperature ranges and other large environments. And you can see here we've actually implemented our systems in a number of programs, both space-based and ground-based telescopes, anywhere from the James Webb Space Telescope to the European extremely large telescope to the GMT, where they've utilized the dynamic interferometer capability in order to perform measurements during assembly of components, during polishing and check of components, to really enable them to monitor and maximize the performance and the accuracy of components within those systems. Here's one example where they were actually performing some cryogenic testing, vacuum testing on some of the mirror segments for the James Webb. You can see in the picture there, we've got a number of the scientists that are performing the operation in quite a large cryogenic chamber with some, definitely meter class optics. And what they're looking to do is they actually wanted to polish the mirrors down. and measure those at ambient temperature, which they could do using the dynamic interferometer, even with the large size of the samples, and large distances. They were able to set up confocal measurements and measure the area of each of those at ambient temperature. And then, as you know, these segments will be operating in space, so they actually had to, drop the temperature on these as well, and then remeasure through a thermal chamber that you can see in the picture in the center here, and then look at the residual and see how those, segments and mirrors changed as temperature shifted. And if they did change, they could again reiterate on the polishing process or adjust as needed. You can see here that in this example, they looked at, the ambient versus the cryo, and you can see within the 3D color maps here, slight variations in the shape of these structures. And they were able to measure deformation down to a few nanometers in those environments, and then be able to correct as is needed for each of the segments. Another application at the James Webb was actually looking at the backplane structure. So they're looking at thermal strain and thermal variation. So the thermal response of the backplane was really key in kind of maintaining the alignment of those segments over certain temperature ranges. And so they used a extremely high power laser system to get reflectivity off of that darker structure there, and measure the shape, actually using what's called an SP type system to measure that structure and how that varied over time. And again, with the dynamic interferometry, they were able to measure that shape and change, from 5 to maybe even 30 times per second, to really get an idea of how things fluctuate over time, and that allowed them to optimize design, correct things to make better uniformity, and other variations and corrections of that nature. Another telescope where the phase cam or one of the dynamic interferometers was used was the Large Binocular Telescope. And here you can see that the interferometer itself is up on top of the structure, and then it goes through kind of a null and CGH simulator. And then you can see that down here at the bottom, the element was mounted kind of in the hexapod to be able to align, and you get quick 3D data where you can look at how the structure is shaped, kind of in the nanometer regime, and allows them to check the performance of their spin casting and what that structure looks like, even on this tall structure. In a lot of cases, you couldn't do that with an interferometer that didn't have dynamic capability, because there's just too much vibration, large structure, and you get a lot of noise, and you wouldn't really be able to get accurate results. Again, we come back to the autocollimation cryo test. So here you can see the customer utilized one of our dynamic interferometers in a pressure vessel. You can see on the left-hand side here. And what they were doing was actually looking at, this telescope and performance, under temperature. And so through within the cryo chamber, they were able to drop down vacuum, and the pressure chamber allows the interferometer to still operate. And you can see that getting, measurements on this and getting to do kind of an autocollimation test where you've got the flat, quite a ways away, and you're looking at how that element changes, through temperature shift. A lot of temperature variation, a lot of larger structure vibration, and the system was able to measure the mirror extremely well, even in this really tough and stringent type of operating environment. One other thing that I'll say on the dynamic interferometers is that they also have the ability to be used on invisible wavelengths, both in the mid-wave IR regime as well as the long-wave IR regime. For mid-wave, that allows you to measure a lot of heat-based sensor and imagers and properties of those systems. The long-wave allows you to measure coarser surfaces. And here on the bottom left, you can see the phase cam midwave IR, where we also have integrated a 150 millimeter beam expander. So you can get a 150 millimeter collimated beam using an off-axis parabola built into the instrument. And again, that allows you to set up in more difficult or invisible wavelengths and still perform these same types of measurements and operations dynamically. The other benefit of dynamic interferometry is that allows for you to make a compact and portable surface profiler. In this case, we've got the Nanocam you can see on the left-hand side there, and this is a portable and handheld instrument. You can see the level on the top that really is meant for looking at localized roughness and optical surface roughness. It is a microscope-based system where you can put various magnification objectives from 1x to, say 50x, getting, fields of view from, 9 millimeters down to 100 microns. And at all of those lateral ranges, you're able to achieve sub-nanometer vertical resolution on surfaces. Some of the applications that this is used in, they've been used in situ in a processing and polishing equipment, as you can see here, where it's mounted on a robot and it pans across and measures the elements as they are fabricated. We've done on-optic measurements. You have a tripod that you can use to align and null out to the surface to measure quick 3D spot checks of surface roughness within seconds. You can do it on large gantries that you can see here, thanks to our friends at Coherent, that utilize it to look at much larger optics. And it can be robot mounted directly. So if you have customized automation or want to have sort of a production type automation where you're looking at multiple samples, we do have the ability to mount that on a robot. And because of that dynamic interferometry capability, even vibration of the part of the robot doesn't affect the performance of the data that you get. Here, what we'll talk about is a quick clip of the handheld device, which is called the 4D Inspec. It's not strictly an interferometer. It uses a similar type of technology called polarized structured light. But again, it's a similar type of dynamic interferometry where you're able to directly measure surfaces even in a handheld type of environment. So you can bring the system out to the shop floor, look in terms of inside engine components, engine bores, look at things like turbine blades and surface pitting, cracking, corrosion. And get micron type resolution in a handheld type device. So again, the dynamic interferometry really opens up different options to being able to bring metrology out into tougher environments where you couldn't really measure directly before. So in conclusion, I just really want to reiterate that dynamic interferometry and the interferometers really open up a myriad of possibilities that were not really practical or possible before, in terms of being able to perform metrology in tougher environments or on tougher type optical setups or systems. And this technology has been critical to the development and the continuance of a number of ground and space-based telescopes, including JWST, throughout the years. A lot of this, they weren't able to really measure without the dynamic interferometry, and so it's quite nice to be able to continue that development and to be a part of the development of those programs. And not only those, but having this ability allows us also to really bring the metrology to the parts. So we don't necessarily have to bring them into a lab to measure. We can take that metrology and that interferometry out to the devices or samples, through portable, robot mountable, or even handheld type means. So again, I'd like to say thank you very much to you all for your time today. I'd also like to thank Laser Focus World for our opportunity to speak today and for letting us be a part of the PhotonicsNXT Summer Summit. Thank you very much.